let's see now some definitions that are useful when we are talking about the metric spaces that we already know, okay? So, for example, we talk a lot about segments. Okay, a segment AB in R is the set of the real numbers such that they are between A and B. Okay, this is the open interval. We can also, in the book, they talk about interval referring to the closed one. Okay, but we can say closed interval, open interval. Okay, the closed one, the only difference is that it includes the endpoints. Okay, A and B are included. We can also have half open intervals, okay? Like AB open on the left or on the right, sorry, or on the left. Okay, in this case, it's just a question of including one of the two endpoints. Okay. So these are the half open intervals. Now, something that is, so a segment is the way we understand continuity and all those notions in R, but then when we move to higher dimensions, the notion of segment is replaced by the notion of ball. Okay, so what is a ball? So if we have, in this case, we are working in RK, okay, and we have that the ball of radius r centered around x, okay, is the set of points y in RK such that the modulus of x minus y is strictly less than r. Okay, so this means the points that are within a distance r from the point x. So if we have a distance r, okay, oops, I was definitely not expecting a solid ball. All right. Anyway. So if we have a point x of the distance r, the ball is the set of points that are within a distance r from that x, okay? And notice that we are leaving out, we're taking every point that is inside this ball, okay? But we are leaving out the boundary, okay? For the closed ball, the closed ball is the same definition, but we need to take the equality case here, okay? So we need to allow the equality. And there is one more notion that we need to remember is the notion of convex set. Okay. So what is a convex set? So let's say we have E in RK is convex. Okay. So convex means that we can read from any given point. We can read all the other points in the set, and the segment that connects those points is contained in the set. So for example, if I do something like this, this would not be convex because then I have points here that I cannot connect with other points in the set. For some I can, but not for all. Okay, sometimes when I try to throw a line between 2 points, part of the line will fall out of the set. Okay, so we need to mathematically describe this. And the way we describe this is that the set is convex, okay, if and only if lambda x plus 1 minus lambda y belongs to E for all xy in E and for all lambda in 0, 1. Okay. You can put 0, 1 in the open interval or the closed interval, okay? Because when lambda is 0, we look here, lambda 0, this sum, this linear combination gives you y, which is on the set E. If you put lambda equal 1, then you get x, which is also in the segment that connects the 2 points, okay? So here what we are doing, as we move lambda, you can think about this like a movie, okay? So as we move lambda, we transition from y to x if we go from 0 to 1, or from x to y if we go from 1 to 0, okay? So this formula we wrote here is describing every point that is in the segment, okay? All right. Another way to write this down would be to write x plus lambda yx, I believe. Okay. All right. It may be xy. You can check that. But if you write it like this, then it's clear that what you're doing is moving from x. Okay. It's x. It's actually xy. You are moving from x, okay, in the direction of y minus x, and you are moving lambda units, and as lambda grows, you are getting farther from x and closer to y, okay? All right, let's see, well, some examples of convex sets. So balls are convex, okay? This is clear geometrically, but let's check. So if we have a ball, that means y minus x is less or equal than r, okay? Let's say we have 2 points inside the ball. Let's say we have x, well, x is the center, so let's keep that as the center, and let's take 2 points, y and z, okay? And we need to see that the line that connects those two is always inside the ball, okay? So let's work on that. So we want lambda y plus 1 minus lambda z, okay, inside the ball of radius r, center x. So this is what we want to see. If this is true for all lambda in 0, 1. Okay, so for that we need to check if the modulus of lambda y plus 1 minus lambda z minus x, okay, is less or equal than r. All right. So how do we check this? So this has a bit of a trick that we use a lot in proofs that are asking to show that something is convex. That is, when we have a coefficient 1, we can always write the 1 as lambda plus 1 minus lambda. Okay, and that allows to write minus x minus 1 minus lambda x. Okay, so then now we can rearrange things here. So this is lambda y minus x. Let me use parentheses here. I want these two to, yeah, I'm missing a lambda here. There we go. Now it will work. Plus, and then 1 minus lambda, and then z minus x. And this goes with parentheses too. Okay. And then the triangle inequality is going to give me lambda y minus x plus 1 minus lambda z minus x. But this, because y and z are both inside the ball, these two quantities are less or equal than r. So I have lambda r plus 1 minus lambda r. And then what do I get here? This is r. And we are good to go. Okay, so then we have shown that actually the linear combination lambda y plus 1 minus lambda z belongs to the ball. Okay, and let's do one last example. What is called about the k-cell. K-cell, that is, these are sets in Rk. Okay, let's call them Q just to make things simpler. Okay, and the way they are defined is the set of points x1 through xk in Rk such that a 1 less or equal than x1 less or equal than b1. There are quantities a1 b1, a2 b2, and so on, ak bk. Okay, that bound each of the coordinates. Okay, we can write it this way, or we can just write, because this is very lengthy, right? So instead of writing the whole thing, what we will write is ai less or equal than xi less or equal than bi for I equal 1, 2, and so on, all the way to k. Okay. But for example, in k equal 2, when k equal 1, we have a segment, right? Would be just one inequality, so that would be a closed interval. But if we have k equal 2, in that case, what we are saying is that each of the two, this would be my x1, sorry, so this would be my x1 that is in between a1 and b1, and then I have x2 that is in between a2 and b2. Okay. So all the points that are in between those two are all the points that are contained in this rectangle. Okay, so this is my Q in this case. So in dimension 2, the K cells are rectangles. And if we go to dimension 3, we have a rectangular prism. It's a shoe box, okay? And in higher dimensions, it's the generalization of a rectangular prism.